Stamitalks.
All right, welcome everybody to a new episode of Stamitalks. My name is Mark Slijzer, and today we have a second appearance of one of our guests, Carmen Perez. Welcome.
Thank you, Mark. Yes, I'm starting to feel like a nitric acid influencer.
Oh, I think you are. You are. You've been. You are a process engineer in Stamicarbon, working with us for about 5 years. And the previous time on the podcast, I think, was on season 1, episode 5. And that was an episode where, together with Pas Mundos, you discussed the nitric acid technology more in general. I think because today we're also going to talk about nitric acid, but on a, let's say, an extension, more on emission reduction. But maybe it's good as a foundation to briefly touch upon the technologies that we offer. So maybe if you can explain a bit about the technology options for nitric acid, I think that's a good way to start.
Of course, yeah. So Stamicarbon has a nitric acid in its portfolio for a long time. And there are more than 40 plants licensed by Stamicarbon, and 20 of these plants are still in operation. And I say still because the last plant was licensed in 1989.
Oh, that's a long time ago.
Yeah. But for some time, Stamicarbon stepped out of the nitric acid business, and in 2017, it was decided to go back to nitric acid. So we brought this old technology back to present, and now it is competitive at the moment. And as we mentioned in the previous podcast, we have monopressor and dual pressure technology. So we are able to offer solutions for all range of capacities. And the main highlight of our technology is that we aim to maximize the energy recovery, and that when we talk about nitric acid is translated into maximizing the steam export.
Okay. So then that's the biggest gain is it's a very efficient process that has, as you mentioned, high steam available for other processes on the chemical side.
Yes.
Okay, so that's good. And you said monopressure and dual pressure. Today we're going to talk about abatement systems, mostly about tertiary abatement systems. That implies that there's also a secondary and a primary abatement system. Can you explain what's the difference between those three type of abatement systems in a nitric acid plant?
Yes. So for that, we need to start on where the emissions of the nitric acid plants are located and where the N2O is formed. So the N2O is formed in the ammonia burner, where the main reaction of ammonia oxidation to NO takes place. And in this reactor, the ammonia is all converted, but it is converted only around 96% to NO, and the rest goes to N2O and nitrogen.
Okay.
And while nitrogen is an inert, so yeah, we are reducing the selectivity towards NO, but still is not a contaminant. N2O needs to be removed before we send the tail gas to the atmosphere.
Okay.
So this is where the N2O is produced, and where it is emitted is in the stack. So there is only one point of emissions in the nitric acid plant, and this is the stack at the end of the plant. And here we emit N2O and also NOx.
Okay. And those two, because I think in terms of emissions, a common term is like the CO2 equivalent. How do those two compare to CO2 emissions?
Yeah, so N2O is the equivalent to 300 tons of CO2.
Okay.
So it contributes 300 times more to the greenhouse effect than CO2. And this means that, yeah, we can get some money also from reducing the emissions of our plant. So we can be sustainable and also get some money back in this way.
Okay. And,
yeah.
So let's see. That's where the emissions are formed. And then how to get them out in the
Yeah. So as you mentioned before, there is primary, secondary, and tertiary abatement. When we talk about primary gases, that is where the N2O is formed. Okay. So in this way, we should modify the catalyst in a way that the selectivity to N2O is reduced. So this means that less N2O is being formed in the platinum gases.
It's really reducing it at the source, basically.
Yeah. Okay. Yeah, that would be the first way of reducing it, but this is limited because at the end, the main objective of these platinum gases is to convert ammonia into NO. So at the end, it depends on the catalyst supplier, and not on a licensor. It's out of our scope. There is some limitation. You cannot reduce N2O completely. There will always be some N2O formation.
Okay, and then you say 96% is converted, so the other 4%, part of that is
N2O,
indeed it is transformed. So let's say out of the full 100%, you always have 1% or something like that that is still
N2O.
emitted. Okay.
Yes.
Okay, so you need something else.
Yeah. And then you could have a secondary abatement.
Okay.
And the secondary abatement is located below the platinum gauzes. So we will need another layer of catalyst to reduce this N2O. And this N2O will be decomposed at this high temperature, because in the burner we are talking about 900 degrees.
Okay.
So it will be at high temperature, and there are some catalysts, I think they are composed of metal oxides. And here you can reduce also your N2O inside the same ammonia burner. The secondary abatement is a tool also for revamping nitric acid plants in order to reduce the emissions. And in this case, temperature doesn't play a role because, well, it does, but it's the same for all processes. It's in the ammonia burner. We always have around 900 degrees. But the secondary abatement has some drawbacks when we talk about revamps, because in most of the cases, this ammonia burner reactor was not designed to hold a catalyst, a secondary catalyst. So in some cases, there is a basket, but it has some alumina balls for distribution.
Okay.
And in other plants, there is not even basket present. So then when we are talking about adding this secondary abatement system, we need to study if the reactor will handle this additional load.
Okay, so it's a mechanical issue.
So in a lot of cases, this is a big mechanical risk because someone needs to take guarantees, but maybe the ammonia burner has been running for 30 years. So the expected lifetime is already passed. And any small modification can have a huge impact, and who will take responsibility. So it has a lot of mechanical risks. And also, the conversion will be limited because for the same reason, the reactor was not designed for this catalyst. So the space that is available is limited. And this means that we can, in most of the cases, we cannot go further than 90% N2O reduction. Okay. And if we look at the trend on emissions, this means that probably in a few years, you still need to go to tertiary.
You need to go to tertiary anyway.
Yeah.
Okay. And then option 3?
Yeah, our favorite.
Yeah.
It will be the tertiary abatement. So the tertiary abatement removes N2O from the tail gas, not from the process gas. And the tail gas is the gas that we get out of the absorption column. So this tertiary abatement system will be located downstream the absorption column. And this means at the end of the plant. So in the tertiary abatement system, we will reduce N2O also over a catalyst. Most of the times we are talking about iron zeolite. And here, depending on the tail gas temperature, we have different solutions. And one of the advantages of tertiary is that since it's at the end of the plant, it can be combined with the NOx removal. So we can remove NOx and N2O in the same reactor.
Okay, so you get 2 emission reductions for the price of 1.
Yeah.
Okay, hey, and then this is, you already mentioned, this is our favorite from Stamicarbon. So yes. I think in all new grassroots plant, this is already part of the process.
Yes, that's correct.
Could you also apply this to revamping?
Yes. So for grassroots plants, as you mentioned, we are offering best available technology. So we always aim to get minimum emissions, and our process is already designed for having tertiary abatement system in place. So we select the temperature at 480 degrees, and that temperature is perfect for reducing N2O without needing any reducing agent.
Okay.
So in the grassroots plants, we have first the N2O reduction, and we do it in the same reactor than the NOx removal, but we have a catalyst where we can remove both of them. We need to add some ammonia for the NOx removal, and we are able to get 99% NOx removal and 98 or 99% N2O removal. Depends also on the client requirements. And for revamp, we have different options depending on the tail gas temperature. So we can implement our standard solution if the temperature goes from 450 to around 600 degrees in the tail gas.
Yeah.
And then if there are lower temperatures, we need to adapt the solution to the plant.
Okay. And then what type of adaptations can you offer?
So when we are talking about temperatures that we call medium tail gas temperature, that would be between 350 degrees and 450 degrees. Then we need a reducing agent. So we are able also to remove NOx and N2O in one reactor and also in one bed in this case.
Okay.
And here we need to add some natural gas or any other reducing agent.
But just adding it, not burning it.
Yeah, only adding it. Yeah, and this will act in the reaction, and we will have some CO2 at the end. But as we mentioned, N2O is 300 times more than CO2.
Yeah. Okay. And then what if I have a plant that runs below 350 Celsius?
And that is a very common situation, unfortunately, because this is the most challenging scenario.
Okay.
But a lot of old plants have very low tail gas temperatures because at that time recovering energy was not so relevant. So in this case, we design a system when we can heat up the tail gas, and then we have to remove the N2O and reduce also the temperature of the tail gas because the abatement system is located upstream the expander. And we need to keep the plant as it is. So the expander also have a maximum operating temperature that cannot be touched. So we design a system where we minimize the impact on the existing operation and on the upstream and downstream equipment. And it consists on heating up the tail gas and reducing the temperature. And depending on the plant, on the utilities that are available on site and on the preference of the client, we design the heating system in different ways, like with electricity or fire heaters, or depending on.
Okay, whatever makes it warmer.
Yeah.
Okay, and so you said there are a lot of plants that have these lower temperature. You also mentioned that Stamicarbon has these plants that are designed for 480 degrees. So basically you can apply this for all different type of licenses, different technologies. It's not limited to Stamicarbon technology only. Is that correct?
Yeah, that's correct. It's true that in the Stamicarbon technology as it is nowadays has high tail gas temperature, but there are also a lot of old Stamicarbon plants that have still low tail gas temperature. So in these plants, we can also implement this system, and also for other technologies the same. Yeah, it's we have solutions for the whole range of tail gas temperature.
Okay, well, that's good. That's good to know. And before that, you mentioned that, so the 6% from global emissions, global greenhouse gas from the industry is from N2O emissions.
Yeah.
Is there any legislation in place to reduce that, as far as you know?
Yeah, we are seeing that in more and more countries, the producers are concerned about N2O emissions, and there is also more pushing from the authorities to reduce this N2O. We see there are also some associations that are helping the producers to reduce these emissions.
Okay.
And at least as we know in the European Union, you can get some money back from reducing your CO2 emissions.
Okay.
And the same goes for N2O. So they applying the CO2 credits, you can get even more from reducing your emissions.
Okay, so there are subsidies available to let's say reduce the capex, I assume, and then also because this reduces your emissions, you also don't have you need less CO2 credits, so also it has a beneficial effect on your OPEX.
Yes.
Do you have some case studies regarding this?
Yes, like last year we prepared a case study, and we were considering a plant of 800 metric tons per day. So that will be dual pressure, medium size plant. And here considering that there is no abatement system in the plant, so all the N2O that is produced in the burner is emitted. And going from that to having tertiary abatement, you could save around 30 million of euro per year.
30.
Yeah, 30.
Okay.
Yeah. And in case that the plant has like secondary abatement that goes to 90%, It is changed by tertiary abatement, so goes to 99%. You could save around 3 million. So the numbers
still
are
significant. Yeah. So then you save the environment and you save money. So it's a very clear definition of a win-win.
Yeah, and here we are considering its price from last year. This was done last year, so I think we are considering 70 euro per ton of CO2.
Okay.
But this price, if we look at the trend, is increasing more and more. So every time N2O needs to be multiplied by 300. So as you see,
I think I've seen some projections of the CO2 credits to go up to 150 and even above that. So
this can be double easily.
It doubles indeed your business case. So that's really good. So basically, I think you've covered quite a lot already. It's you've explained primary, secondary, and tertiary abatement. For tertiary abatement, you can do this for 3 different tail gas temperatures. For each, you have a solution, and the higher the temperature, basically, the more easy it is. And by implementing this, you can really save money and save the environment. So basically, why wait? That's the overall. And then there are subsidies available as well. So I think that summarizes a bit what we've discussed so far. Did I miss anything, or do you want to add anything?
Yes, one thing I want to add is that we will most likely see our first tertiary abatement in place soon. So we already finished our part of the project, and now the tertiary abatement system is being built, and it will be implemented in Mexico for N2O reduction. And in this case, the plant was not Stamicarbon technology, and it was high tail gas temperature, so higher than our standard, 550 degrees. And it's a system designed for only N2O removal. And hopefully it will be in operation soon.
Okay, well, that's a really nice note to end this podcast. Thank you so much for explaining and being again a part of this this podcast.
Thank you.
And also thank you to our listeners. Thanks for tuning in to Stamitalks, and we hope to see you next time. Thanks.
Thank you.
Stamitalks.